plan to do today is to very quickly discuss those issues in the mathematics that underlies general relativity that I had intended to discuss last Wednesday, and that I didn't get to, and that you have already read about and done problems on. But I want to say just a little bit about those issues to provide some additional perspective. And then after that, I'm going to talk about the about physics in the sense of particle motion, the equation of geodesic deviation, which I've already talked about once very quickly. Then the Einstein field equations, well, the stress energy tensor, which enters into the Einstein field equations, the Einstein field equations, and then I will talk about, as a consequence of the Einstein field equations, the wave equation that the Riemann curvature tensor satisfies when it's propagating through an otherwise flat space-time, so for weak gravitational waves. And if I have time, and I'm going to try hard to get there, I will then, from that wave equation and other properties of the Riemann tensor, I will deduce the nature of gravitational waves, the basic physical nature, and the simplest mathematical description. My way of approaching this is not in any textbook. In textbooks, gravitational waves are handled by taking the metric of space-time, doing a perturbation around flat space-time, working hard to get rid of the gauge degrees of freedom, finally pulling out the physical aspects of the wave, and then getting to the bottom line I will get to. The way I'm going to do it is much superior, but it has not made it into the textbooks. And it's like doing a wave equation for the electric field or the magnetic field instead of doing it for a vector potential. You do it for something that has no gauge arbitrariness in it, and you don't have to deal with issues of gauge freedom and those complications. And so that's where I want to get at the end of the lecture. That might hang over till Monday, but I will try not. Okay, so any questions? Okay. So let me just say a few words about the commutator. You have read about the commutators. And from your reading, you know that, a commutator of two vector fields is most simply described by regarding the vectors as directional derivatives along themselves. And I talked last time about that isomorphism between the vectors and the directional derivatives, and the fact that a mathematician would say the vector is the directional derivative. And so now you have derivatives, and you know what a commutator means for derivatives. It's you apply these to, say, a scalar field in one after the other, but in opposite orders, like that. And the bottom line, if you go through this calculation, is you discover that this is itself some directional derivative acting on psi. So this itself, this commutator, is also a vector field. And you've seen that in your reading, and you've worked with it a little bit on the problem set. In the reading, there was some discussion of the geometric meaning of this commutator. And I want to comment on that. So you have some point in your manifold. And I want to now think about A and B being very short vector fields, so I can think of them as lying in the manifold. But I will return to that delicate issue in a moment. And so I lay out then the vector A at point P, and I lay out the vector B at point P. And then I go from the tail of A to the tip, and this is another point in the manifold, and at that point I look at what does B look like. And it's changed. It's a little bit different up there from what it is down here. I go from the tail to the tip of B, and I look at what A looks like, and it has changed a little bit. Now, the failure of those two to meet is a consequence of the fact that these are vector fields and they're changing from point to point. But obviously that failure of these, the tips to meet, is something that's second order in the linear size of this little diagram. If I shrink A and B down, then if you think about it for a few minutes, you recognize that this gap will shrink as the square of the size of the diagram. If I cut the diagram, if I cut B down by a factor of 2 and A down by a factor of 2, this commutator will get smaller, or this failure to close will get smaller by a factor of 4. That is obvious from the fact that the definition that involves something that is involves a product of an A and a B, basically. If I cut A down by a factor of 2, I can pull that factor of 1/2 out from out in front by linearity, and I can pull a factor of 1/2 out in front by linearity, and I get a factor of 1/4. And so the failure to close is something that really is goes as the second order in the size of the diagram. And that means that when we draw something like this at second order in the size of the diagram, we can talk about the failure to close. And that failure to close turns out to be just the commutator. So that's just a useful thing to know. It's not something that I'm going to use particularly in this course, but it does underlie the fancy mathematics associated with Riemann curvature when you do it in a particularly fancy way. Okay, so that was one point I wanted to make. Yes?
Is there any way to treat it rather than with the partial derivative notation, the actual derivative notation?
This is the simplest way to do it. And this is the way a mathematician would do it, because a mathematician would say that this is the same thing as that.
Okay, but if it's the same thing, is there any way to do it using the expression?
I've never thought about how to do it any other way than this, because for me, a vector is a directional derivative. I'm sure there is, and I'll invite you to think it through. But this is the way I've always thought about it. And but I suspect that if you go to older relativity textbooks, you'll find it discussed in some other manner. But I don't know whether that's true or not. Now, there are two types of bases. There are bases that are coordinate bases, which we've talked about, and there are non-coordinate bases. A coordinate basis has the property, obviously, that the commutator of the basis vectors, because the basis vectors are just derivatives along the coordinate directions, and they're just partial derivatives, and partial derivatives commute mathematically. The commutator vanishes. If we have a coordinate system, and so this is, say, x equals 1, x equal 2, x equal 3, that's y equal 1, y equal 2, y equal 3, then the basis vector ex basically is tangent to this curve, and it reaches from x equal 2 to x equal 3. That's the basis vector d by dx at fixed y. It moves along a curve of fixed y, and it reaches, at least in the small, if this were a diagram that was really small compared to the curvatures that are present, it would be reaching precisely from x equal 2 to x equal 3. So, and similarly, d by dy is the guy that looks like that, and up here I can go through this process of drawing the diagram that goes into the commutator. And just because this is a coordinate system, this little diagram closes. And so you see geometrically, because this basis came from a coordinate system, we are guaranteed closure, just geometrically, at second order if you think it through very carefully. Whereas in general, we will not be guaranteed closure. For non-coordinate bases, in fact, it will be true that the basis vectors will not commute, but the commutator will be itself be a vector, and so it can be expanded in terms of the basis in this way, and the coefficients are called the commutation coefficients for this basis. So, for example, for the orthonormal basis associated with a circular coordinate system on the blackboard, which is something you worked with on the problem set, you can easily see that the commutator is non-zero. In fact, there's a theorem that follows basically from the diagrams that I've drawn here, or the mathematics underlying the diagrams, that say a coordinate system or a basis is a coordinate basis if and only if the commutation coefficients vanish, if and only if the basis vectors commute with each other.
So any vector can be written as partial coefficient.
So any vector can be written as any vector can be expanded in any basis.
Okay, but any vector can be written as a directional derivative.
Any vector can be written as a directional derivative because.
So why can't we write d mu and d nu as directional derivatives and then just have them commute the same way?
Okay, so let's look at it this way. Suppose that you go onto the surface of a sphere and you introduce spherical polar coordinates. One of these among the coordinate, let me start over again. The coordinate basis is d by d theta and d by d phi. And so here is d by d phi at fixed theta. Here's d by d theta at fixed phi. Okay, well, but let me finish this if you're fine, nevertheless. So that's d by d theta at fixed phi. This is d by d phi at fixed theta. And you may recall d by d phi at fixed theta is just the angular momentum operator, aside from a factor of I, associated with the z component of angular momentum in quantum mechanics. Now you can go in and introduce on the surface of this sphere, similarly, a spherical polar coordinate system where it's done around the x-axis. And we have here then a basis vector that's the analog of d by d phi. The basis vector is d by d, let's call it d by d psi at fixed epsilon, where my coordinates now are psi running like this and epsilon running down there. And so you could ask yourself, could I use, I can surely go in at some point here on the sphere, and I can use d by d phi and d by d psi as basis vectors. Here's d by d phi at fixed theta. Here is d by d psi at fixed epsilon. This guy is also the angular momentum operator in quantum mechanics for rotation around the z-axis. This is the angular momentum operator in quantum mechanics for rotation around the x-axis. And I can certainly use that kind of a basis. But these guys don't commute. And the reason they don't commute is that d by d phi is a basis vector at fixed theta. D by d psi is a basis vector at fixed epsilon. They're not associated with the same coordinate system. They are basis vectors that this is a coordinate basis in the theta phi coordinate system. This is a coordinate basis vector. This is a coordinate basis vector in the upsilon psi coordinate system. Those are two different coordinate systems. And if you go in and mathematically ask yourself about the commutator of this generator of rotations around the z-axis with the generator of rotations around the x-axis, they don't commute. The commutator, in fact, is a generator of rotations around the y-axis. So this is a little example, which is worth thinking about a bit, that illustrates then that the key thing about a coordinate basis is not merely what you're differentiating with respect to, but also what you're holding fixed. Okay, that sort of answers the question you asked. But, yeah.
If instead of 1 over r d by d theta, you pick d by dr and d by d theta, so those two things?
Yeah, because they're partial derivatives, and they're associated with a coordinate system.
Okay, so as long as you don't try to scale it so that it's an orthonormal system, you get coordinate basis.
Yeah, but you can be non-coordinate for other reasons.
Cool.
Yeah. Right. Okay. So in this course, we will be using two kinds of bases. We'll be using coordinate bases, and we'll be using orthonormal bases. The reason we want coordinate bases is most calculations are done most easily and most clearly in a coordinate system, and in the basis that's associated with the coordinate system, in fact. And so in the coordinate basis associated with that coordinate system. On the other hand, when you want to do a physical interpretation of some measurement, you want to be using some orthonormal basis where the time basis vector has unit length, the spatial basis vectors have unit length, and they're perpendicular to each other, so you can think about things in the manner that you do in special relativity. And so for physical interpretation, we will always use orthonormal bases, but for calculations, we will always use coordinate bases. Well, not always, almost always. When you get sophisticated in general relativity, you find that, in fact, many calculations are done most nicely in orthonormal bases, in non-coordinate bases. But you have to be somewhat sophisticated in the subject to really use those well. You're accustomed to using these kinds of bases in Jackson, for example, in electrodynamics, for spherical polar coordinates and for cylindrical coordinates. But you're accustomed to them because somebody derived the relevant formulas for the curl and the gradient and the divergence, and they've given them to you. Or maybe you derived them for yourself at once, and you use them once and for all. But if you're doing calculations where it's just not plug-in and grind formulas, then it requires a fair degree of mathematical sophistication to work with non-coordinate bases in calculations. And for that reason, in calculations in this course, we will almost always work in coordinate bases, physical interpretation in orthonormal bases. Okay. Questions? Now, another issue that you have read about is how you compute the connection coefficients from the metric and the commutation coefficients. So the connection coefficients, you'll recall, are not defined until you have introduced a basis, and then they are defined by the fact that the derivative along a basis vector of another basis vector is this connection coefficient times a basis vector. So that gave us the connection coefficients, and then, but one often needs to know values of the connection coefficients. You can sometimes deduce them just by drawing pictures, and I asked you to do that in one case in the problem set. But quite generally, the way you can compute them, there are other formulas and other ways to compute them, and a sophisticated person won't do it this way. This is the simplest way to describe it. And that is that you compute this connection coefficient from a guy that is has all of its indices down like that. And then you compute, but before that, you need to know what the connection coefficient with all the indices down is. And the precise formula is written down in your reading, but it has the form 1/2 metric coefficients with a partial derivative plus metric coefficients with a partial derivative minus metric coefficients with a partial derivative. And then you have plus connection coefficients with all indices down plus connection coefficients with all indices down minus connection coefficients with all indices down, where these indices are nu, alpha, and beta in some appropriate order, which you can go read about. The way that I do the mathematics, the ordering on the C's is identically the same as the ordering on the derivatives of the G's. That's because I have defined the connection coefficients with indices down as being obtained by lowering this last index on the commutator. Now, warning for those of you who go into the theory of Lie groups at some point in the future, connection coefficients are defined in the theory of Lie groups in precisely the same way as we do, but the notation in the theory of Lie groups, this index comes first and not last. And if you lower it in the theory of Lie groups, it gets lowered down, and so the indices, and it gets lowered down and is first, not last. The conventions are different, and the reason that in relativity we generally use a different convention than in the theory of Lie groups is so this formula will look the same for the C's as for the G's, so you don't have to memorize two different conventions for those. Okay. Okay. Curvature. I introduced curvature in the reading in the simplest way that one can. The Riemann curvature tensor is a measure of the failure of double gradients to commute. That's one aspect of Riemann curvature, and it's the simplest way to define it. And so if I use slot naming index notation, then the Riemann curvature tensor can be written in this way. You take a vector field A, and you take a double gradient on it, and then you take that vector field A again, subtract it off, with the two slots in the opposite order. So you're changing the order of the gradient slots. Now, if these were partial derivatives, the answer would be 0, because partial derivatives always commute. But they're not partial derivatives, and as I had warned you earlier, when you're taking one derivative, you're really not sampling curvature of the manifold. The influences of curvature show up only when you take two derivatives, and it shows up here then. And this fails to commute, and it fails by virtue of having curvature of the manifold. And so I can write this in the following way. I have indices mu and nu, and this is antisymmetric on those two indices, and I'm going to put those indices last. Then I have an alpha index, which I will put here. Then I have a beta index there, A beta. So I've lined up the indices. I've put the mu and nu last, so I'm antisymmetric on them, obviously. And then this is obviously ought to be linear in A. And so this is something that's linear in A, and it has one free slot, A alpha, so it's a vector on that slot. That is one free slot alpha here, which corresponds to that alpha there on the A's. And so I've taken in this course this to be the definition of the Riemann tensor. And then I wrote down in the reading, and I gave you a not entirely simple problem to compute what the Riemann curvature tensor is in terms of the connection coefficients, and then there turns out to be one commutation coefficient hanging off the end if you're working in a non-coordinate basis. Okay. The key thing to remember is that the Riemann curvature tensor looks like something that is a connection coefficient with a derivative minus connection coefficient with a derivative, these being commas being a partial derivative in a coordinate basis, or it's the coordinate basis acting as a directional derivative on this, or a scalar. Then you have plus a product of two gammas minus a product of two gammas, and then there's a plus a gamma and a c. So it has a structure that looks something like this. But the key thing that I want to get at here is when we compute Riemann curvature tensors, we will almost always be doing it when we, in a coordinate basis. And in a coordinate basis, then the c's are not present, only the g's, because the connection coefficients involve the g's with one derivative on them. And we're taking a second derivative. This looks like a metric coefficient with two derivatives on it, plus a bunch of nonlinear terms. And the nonlinear terms are where the richness arises from in the Einstein field equations and in general relativity. It's a highly nonlinear theory, and those nonlinear terms play a major role. But if you have a very weak curvature, then all that's going to really matter is the g with two derivatives on it. And in the reading, you see a formula of that sort for the Riemann tensor. This Riemann tensor plays a number of other roles. I will write down in a few minutes the equation of geodesic deviation, where it enters in as the thing that produces then the tidal gravitational forces in a Newtonian context, or in the case of a gravitational wave. It also turns out, and you can go look in the reading in Schutz or in MTW, to be associated with the fact that if you take a closed curve, for example, you take a closed curve formed by, in this simple example, by great circles, so the equator of the Earth, and then curves of constant longitude, and you take a vector, and you parallel transport it along this closed curve. So let me take that vector to be like this, and parallel transport along a geodesic. It's going to remain tangent to the geodesic. And then you carry it up this leg, and then you carry it back down this leg, parallel transport. And when you get back down, it has changed. And so if you parallel transport a vector around a closed curve in a curved manifold, that vector changes. And when this closed curve around which you do the parallel transport is very small, the change in this vector is just, again, given by something like this, the Riemann curvature tensor contracted into the vector, basically, times something that tells you what curve you transported around, which has to do with these indices mu and nu. So I'm not going to write down the formula, I'm just telling you that it is the Riemann curvature tensor when you have a small closed curve that tells you about this change, and you can go read about it in standard textbooks. I won't use that, but it's something you should be aware of. Okay. Any questions? Now, the Riemann curvature tensor has a number of mathematical properties that you will be using on the problem set that I will give you for next week in connection with studying gravitational waves. Obviously, it's anti-symmetric in the last two slots by this defining formula. What that anti-symmetry means, if I want to say it in abstract notation, is that if you stick a vector A into this slot and a vector B into that slot, you'll get a minus the result that you would get if you stick B into this slot and A into that slot. So that's the meaning of it. In terms of slot naming index notation, it says R mu nu alpha beta is equal to minus R mu nu beta alpha. If you interchange the slots or interchange the order in which you put vectors in the slots, you pick up a minus sign. This formula then has two meanings. In slot naming index notation, it's equivalent to that. But if you have a basis, and these are components on a basis, it just means that the numerical value of this component in the basis that you happen to have for fixed mu nu alpha beta, for example, this might be 2, 1, 0, 3. The numerical value of this will change by a sign if I change the values here. So R2103 will be equal to minus R2130. So that's the meaning in terms of components in a basis. The meaning in terms of slot naming index notation is this. So that's one symmetry. So let me write it down here in slot naming index notation. It turns out that this is also antisymmetric in the first two slots, but proving that is not trivial. And so this is minus R nu mu alpha beta. If you interchange the first two slots, you flip a sign. And it turns out also that it is symmetric if you interchange the pairs of slots. And so it's also equal to R alpha beta mu nu. So you take the pairs and interchange them, and the Riemann doesn't change at all. You interchange the first two, it flips a sign. You interchange the last two, it flips a sign. So those are just useful properties. And then another useful property is something that is called the Bianchi identity. Which says that if you take a gradient and then you permute these last three indices, let the first two indices stay the same, so I'm working only on the last three indices. One of them is a derivative index, the other two are not. It was already antisymmetric in this pair. This is that the sum of that, this plus alpha, beta, gamma, and I'm going to permute these, so I'll go delta, epsilon, gamma, just pulling the gamma around to the end. So alpha, beta, delta, epsilon, semicolon, gamma. And then I'm going to do the same thing. I'm going to pull the first one around to the end again. Plus R, alpha, beta, epsilon, gamma, delta. So that's 0. If I repeat this again, pull the epsilon around to the end, I get back to where I started. So these are a series of mathematical properties of the Riemann tensor that are very useful. It turns out that this set of properties, these symmetries, imply that although you might have thought that the number of independent components here of Riemann would be 4, because the first index can take, in space-time, can take values 0, 1, 2, or 3, so there are 4 possible values, times 4 for the possible values of mu, times 4, which is 256. So you might have thought there are 256 independent components of Riemann. It's really a rich tensor. In fact, because of these symmetries, there are only 20 independent components. So it's not nearly as rich as you thought, but it's still rich enough to be interesting and rich enough to be complex. Okay. Okay, any questions? Yes?
Is the antisymmetry expected to teach in pairs, or can you, for example, can you flip the mu and the beta, or do you have to flip them?
No, you have to flip the first two and you get anti-symmetry. The last two you get anti-symmetry. There is no symmetry at all connected with anything where you flip one of the, where you take one from the first pair and one from the second pair and try to interchange them. There's no symmetries at all there. I guess I also want to introduce the Ricci curvature tensor because we will need it when we talk about the Einstein field equations. R alpha beta is what you get by contracting on the first and third indices of the Riemann tensor. That's called Ricci. And this is the convention I use in some textbooks, some communities. Mathematics or physics, one contracts on the first and fourth indices. But since you're antisymmetric between exchange of the third and fourth, that alternative convention just means that they have the opposite sign for the Ricci tensor. So in this subject, mathematics or physics, you have to, when you're reading what somebody writes and you want to get signs straight, you have to worry about what are their conventions on the Riemann tensor. They may have used opposite signs for the Riemann tensor. They may have used opposite signs for the Ricci tensor. There are a number of possible combinations of signs, and there is no universal agreement on what's best. Okay. And then we have a scalar curvature, which is obtained by contracting the Ricci tensor on two indices. Okay. Okay, so I'm done with the mathematics and want to move on to doing a little bit of physics if I can.